Okay, welcome back. We were just talking about how an ISDN line was two of these channels together. There are some problems with this whole concept of point-to-point, so let's just talk about the problems. First of all, when I do point-to-point, I really can't aggregate. In other words, let's just say, for example, I had a building over here that had two tenants in it, and a building over here that had the exact same two tenants. But, they were competitors, doesn't matter. One's a shoe store, one's a financial organization, doesn't matter what it is. And this guy wants to talk to the second floor of this guy. And this guy wants to talk to the third floor of that guy. When essentially, if it's point to point, you'd have to run two cables. One for customer A and one for customer B. So if you're the phone company, you'd be thinking, well, this is dumb. Wouldn't it be somehow cool if we could just string one cable between the two buildings? And then we could share that cable? Wouldn't that be kind of cool? Well, point to point, you can't do that. Point to point basically means that I can't aggregate routes. I can't aggregate customers. I can't do any cost sharing. Now, because I can't do cost sharing, that means those individual leased lines, as they used to call them, were very, very expensive because there was only one customer paying for it. But if I had 100 customers paying for that same cable, then my price would be 1/100th of that, right? Cool. Okay. So a separate link for every location. So if you only had like 4 locations and you had, wires going to all 4, in a little box diamond kind of a thing, that's okay. You're not really bad off. But if you had 6, 7, 8 buildings you need to connect to, so you wanted to configure it so each one of the buildings could talk to the other 7, wow. The number of cables to pull that off, it goes exponential in one heck of a hurry. So that is just not scalable. And then, after all that, the actual link usage, the how much usage you're actually getting out of that is pretty doggone low per link. In other words, if I have 4 buildings and I'm using 6 cables to connect them together, I'm willing to bet that there'll be a point in time where half of those cables don't have any conversation on them whatsoever. So very, very poor utilization. So that's the problems associated with point-to-point. Does that sound like a test question to you guys? I'm just checking. So the solution to this is on page 331, where they talk about multiplexing, statistical multiplexing. So instead of running 2 cables between the buildings when you had 2 customers, you would have those 2 customers share the cable. You didn't even need to tell them that you were sharing it. It's all done by magic. They thought they had a dedicated line between point A and point B. Shh, don't tell them. But that really wasn't the case. You were sharing that line with some other customer in that building. Cool. You charged them the same. But you didn't have to run 2 cables now. You only had to run 1. So basically, multiple packets from different sources sent along the same cable. Just multiplexing. We've talked about multiplexing before. And again, this was a money-making opportunity. Why string dedicated cables duplicates when I can share a cable? The railroad industry went through this. Each railroad had to have a rail line from St. Louis to San Francisco. And so if there was 4 rail lines, you had to 4 rail companies. Heaven forbid they would actually share. And so there would be 4 rail lines running side by side. And somebody said, this is pretty dumb. This is too expensive. Why don't we all get together and share the same rail line? Okay, same scenario here. Okay, so here's a figure. And basically using the, so here I am over here. I'm customer number A, and I want to send a message over here. Yes, I could pay for the entire T1 line all the way across the entire globe. And this guy over here, B, wants to talk to B. Yeah, we could string those wires, and the phone company would be just glad to send us a bill. But wouldn't it kind of make sense if we had some sort of an aggregation point, like in California, and some aggregation point here on the East Coast? And so these 2 guys actually seamlessly got thrown into a common cable and then split out when we got to the other end. It looked and acted just like you had a dedicated line. From a performance point of view, very rarely could you ever tell that you did not have 100% of a cable. Okay, so that's how it works. Again, the highway analogy, the carrier access point, and then the T1 would be sort of like the getting off of the interstate going onto a state highway, and then maybe you went down to county roads or your driveway when you got down all the way. Okay, so you remember how the internet traffic is typically very bursty, meaning if I'm surfing the web as an example, I'll click on a link and then it'll have a burst of activity and then a flood of activity down, and then there's periods of time where absolutely nothing is happening. So very bursty nature. Because of that, it allowed these companies to bond these two things together and no one even noticed. So it was pretty easy to leave room for other traffic to slip in without affecting any performance whatsoever. And from a cost perspective, this means I'm getting more utilization out of that link. If you said, well, how much is it going to take to build that brand new line between point A and point B, and the accountant says it doesn't really matter how much it costs because we have 7 new customers who are going to come in here and use it 100%, and we're going to be able to amortize this and blah 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 blah. It's the same story of what you're saying is I'm getting ready to have a new flight from Chicago to Chicago to St. Louis, and I'm guaranteeing that all the seats are going to be filled at all times. Okay, so increasing the utilization is a money-making deal. It's not necessarily good for you as far as, because if you exceed that amount, you're going to be impacted by performance. But from their perspective, yeah. Now, just to drive home this point from east to west, okay, so, right, there's time zones, correct? And so if my utilization at 8 o'clock in the morning versus my utilization at some other time of the day, so what typically happens is there'll be a very high utilization on the East Coast early in the morning and very low utilization in the evening, and vice versa for the two coasts. So isn't that just doggone cool that my total link, the aggregated volume of data going through that link going east and west really, really helps me out on utilization? Because otherwise I'd get a business peak in this time zone, a business peak in this time zone, a business peak in the time zone. Now, all right, now I'll admit, if you were talking about a cable that went north and south, right, from New Orleans to Chicago, all inside the same time zone, well then you don't get this. Okay, this is kind of a unique scenario where you're going east and west, where you have time zones, and so the business patterns actually help you with your utilization. Kind of cool. So they talk about virtual circuits on page 333, because how the mechanics of how they do this is through what's called a virtual circuit. So they spend just a few minutes describing what the heck a virtual circuit is. Okay, so let's just assume that I'm back to here, and I've got these two guys' traffics, and I'm combining them together. How the heck do I tell them apart? I mean, I don't want these conversations to get mixed up, right? I have to have some way of identifying the traffic inside this common pipeline that went across the coast that's carrying two conversations. I got to have some way to keep them separate. And so they created this thing called a virtual circuit and a virtual circuit ID. So the idea is that I have a unique number that's assigned to these things that says this is, circuit number 44 and here's circuit number 12, and they're both running through the same physical cable. Okay, now the weird part about this, you remember the talk about the autonomous systems from a couple of chapters back? These virtual circuit numbers are really just inside your autonomous system. So if I go from one autonomous system to another in order to get all the way across the coast, I would be getting another virtual circuit number. In other words, the virtual circuit numbers are not magical in any way. They're just a unique number that's used just for that carrier to get across just its statistical multiplexed cable. Okay. So statistical multiplexing is kind of sort of how it worked. Okay, so to talk about the technique we use to accomplish this statistical multiplexing, the first example is going to be X.25 on page 334. So essentially, the technology we're using on this link, and we're going to talk about X.25, we're going to talk about frame relay, we're going to talk about ATM. But right now, what we're doing is we're pulling off a virtual circuit and sending it across this thing. Okay, so X.25, and this is kind of in chronological order, X.25 was made the assumption that the link quality was absolutely horrible. And to tell you the truth, at one time in the 60s and 70s, and that was a pretty good assumption. The link quality was really, really poor. You know, the longer the distance, the worse off your telephone call, if I'm using that as an example. No. You called grandma on the phone and you weren't absolutely certain if she could hear you or not. You had to scream, "Yes, 12," for her to hear you. Relatively slow by today's standards, 56K up to about 2 meg. And again, it was designed for accuracy above all. In other words, it was designed to think about like a banking scenario where I'm sending money across the wire, right? Where I don't really care how long it takes or how many tries it takes to get there, but accuracy is absolutely premier. So if I'm sending it over a really dirty link, I don't care if it takes 10 minutes to get there or 10 seconds to get there. It's got to get there intact. That's what X.25 is all about. X.25, I'm not going to get into the mechanics of it, but X.25 was all about how to get a link many miles, assuming that the link quality was absolutely horrible. Okay, so things kind of sort of improved, and so the long distance lines were a lot better, and the infrastructure improved dramatically, and so we switched over to frame relay. Frame relay is the next one, and it's essentially the same as X.25, except that X.25 was just like a TCP packet. Every single packet you sent, you waited until you got an acknowledgement back to say it's okay. That's not mechanically, that's not how it did it. But there was a frame by frame acknowledgement that took place. Finally, we got to the point where, we didn't need to do a frame by frame relay. Maybe we could just send checksums occasionally and ask it to verify that things are working. So frame relay was identical to X.25, except we just dropped off that frame by frame checking. And of course, the reason is because the networks got better and we just didn't need to do frame by frame checking anymore. It just wasn't required. And of course, it was a bit faster. It went from 56K up to about 45 meg per second. So backwards compatible with X.25, and then from there on, and X.25 is oddly enough still being used in some areas. It's like there's Eastern Bloc, in Europe, and some of these underdeveloped places where the phones are absolutely horrible. X.25 is alive and well. Not in the US, but it is elsewhere. Then the last one is ATM. And no, we're not talking about an automated teller machine. It's asynchronous transfer mode. Now, the cool thing about ATM was this was designed by the phone company during the time of voice, right? And they said, well, let's build us a network that'll work for everything, because I don't want to have to build two networks, one for voice and one for data. Let's just build one and bolt them all together. Dang good thinking. Okay, we've reached a good place to stop, and we'll pick this thing up again in just a few.